Hello, everyone, and a huge welcome to Kognito. I am absolutely thrilled you're here today. We are looking at something truly fascinating. Have you ever wondered what actually happens, mathematically speaking, when a massive power grid experiences a sudden chaotic fault? Okay, let's dive right into this explainer, and we'll discover exactly how electrical engineers take all that grid chaos and dissect it into perfect calculable order.
To get there, here's our quick roadmap for today. First, we'll look at unbalanced power system faults. Second, defining sequence networks. Third, we'll break down the positive, negative, and zero components. Fourth, system fault calculation. And finally, number 5, applying Thevenin's equivalent. Let's get started.
Section 1. Unbalanced power system faults.
I want you to picture a massive power grid. It's humming along perfectly smooth, right? But what happens in that fraction of a second when, say, a tree takes down a major line or lightning strikes? Well, that is our core problem right there. A fault puts the entire power system into an unbalanced state of operation. In the real world, these faults create a wildly chaotic mess of currents and voltages. It's literally a dangerous electrical crisis, and grid engineers have to somehow calculate, isolate, and resolve it instantly.
Section 2. Defining sequence networks.
Now, what's really interesting about this is how we solve that unbalanced problem. Engineers use a very specific theoretical solution. Let's look at the definition here. A sequence impedance network is a balanced equivalent network for a power system under imagined working conditions, so that only a single sequence component of voltage and current is present. To put that in simpler terms, because calculating pure chaos is, practically impossible, engineers use this mathematical tool to basically swap the chaos for symmetrical, balanced components. This lets them compute unsymmetrical faults at literally any point in the network.
Moving right along to Section 3. Positive, negative, and zero. So what actually makes up this mathematical tool? Think of it like anatomy. Every power system basically has 3 sequence networks carrying 3 sequence currents. First up, the positive sequence. This determines load flow and symmetrical faults, and it carries a positive impedance sign. Second, the negative sequence. This represents the unbalanced faults, and its impedance carries the exact opposite sign of the positive. And third, the zero sequence, where flow is caused solely by the fault point voltage. These 3 components interconnect in these beautifully complex ways to represent any unbalanced fault condition you can imagine.
Let's zoom in on that positive sequence network for a second. It's used in the analysis of symmetrical faults and really forms the foundation of load flow studies in the power system. It's essentially the same as the standard sequence reactance or impedance network. So the crucial point I want you to take away is that this positive network acts as the baseline. It represents the normal, healthy operation and power flow of the grid.
Now, when we contrast the positive and negative sequence impedances directly, we realize they're remarkably similar in structure. The defining difference is purely mathematical. The negative sequence network carries the exact opposite mathematical sign to that of the positive sequence impedance. And then we have the zero sequence network. Now, this one is kind of unique. It's internally free of the fault point itself. In this network, the flow of current is caused entirely by the voltage at the fault point. It's essentially a strict cause and effect relationship, you see. Zero sequence current only flows here because that specific fault point voltage has suddenly appeared out of nowhere.
Let's move to Section 4 and see how this builds. System fault calculation.
So how do engineers practically apply these 3 sequences when a disaster strikes? Well, it happens very logically in 3 steps. Step 1, the system enters its chaotic, unbalanced state because of a fault. Step 2, we mathematically erase that unbalanced mess and replace it by injecting 3 perfectly balanced sequence sets, the positive, the negative, and the zero. Step 3, the post-fault voltage and the actual current are finally determined by calculating exactly how the system responds to each of those individual clean sets.
When calculating these currents, direction is absolutely vital. The main current, which we call IA, flows from the system directly into the fault. Therefore, its sequence components, 0, positive, and negative, represented mathematically as 0, 1, and 2, they actually flow away from the fault point, which we label F. Meanwhile, Z0, Z1, and Z2 simply represent the total equivalent impedance of each respective network, all the way up to that fault point F.
Finally, Section 5, applying Thevenin's equivalent.
This brings us to the ultimate modeling tool that engineers use to radically simplify what would otherwise be a total mathematical nightmare.
Using the Thevenin's equivalent circuit approach, each complex sequence network is replaced by a simple equivalent circuit strung between just 2 points. Point 1 is the fault point, point 2 is a zero potential of the reference bus, labeled N. By doing this, an infinitely complex network is beautifully reduced down to just a single voltage and a single impedance inside a neat, calculable box. It's pure genius.
And this brilliantly illustrates the stark contrast between our networks. For the positive network, the Thevenin voltage is the actual pre-fault open circuit voltage. But for the negative and zero networks, their Thevenin voltage is completely different.
Let me emphasize this because it is absolutely crucial data. The Thevenin voltage for both negative and zero sequences is exactly zero in a balanced system. Why? Because those negative and zero sequence voltages simply do not exist when the grid is in its normal, perfectly balanced pre-fault state. They're basically mathematical ghosts, right? They only materialize when things break down.
So, I want to leave you with this provocative thought. If these incredible sequence networks can distill massive, chaotic electrical failures into simple, zero-voltage equivalents, how might these very mathematical models be running silently right now to secure the massive grid powering your city? Thank you so much for learning with me today on Kognito Key. If you found this explainer valuable, please subscribe to the channel and definitely like and share this explainer with others. Keep learning, and I will see you next time.